Hi everyone, welcome to the Italian C++ Conference 2021. This is Marco. I'll be your host with Alessandro, Riccardo, and Stefano. Hi everyone. So hi Alessandro and Rick. How are you doing today?
Hi,
Hi.
I'm doing great, thank you.
It's kind of
And
it's kind
you?
of it's kind of early today for our conferences, but it's worth it definitely. So
We are very
Right,
excited
yeah.
to be here.
I know that for most of you watching the session, at least from Italy, summer is coming, and we have we have all the openings after, let's say, after the pandemic. It's not really after the pandemic, but I know it's kind of demanding to stay here with us today, and also will be a long journey because we have 10 hours conference in front of us. So I know it's kind of demanding, but it's definitely worth it. So thanks a lot for staying here. And okay, so let me give you a brief introduction to this conference. Very happy to host it. And I think in the last few months, well, in the last year, we got some experience in organizing these online events, and we had the Italian C++ Conference 2020 last year. Was the very first major C++ event turning online, and we had it on Discord and YouTube. We noticed that the integration was not so smooth, so then we opted for going to Remo, as all the other major conferences did. So with the C++ Day, with all our online meetups. Also, I had the opportunity to create this new community about machine learning in my district here in Modena. So we organized lots of experiences online, and so we got some experience, and most of them were very, very, very satisfying, in my opinion. But actually, I'm really missing this this kind of things. I'm really missing the physical proximity, and I really hope to get back to this very soon. That's my that's my feeling for next year. I hope that next year we'll be able to do something like this, probably with some restrictions, with some special special things, and I really hope to get back to this, especially because I'm really missing this. I'm really missing the buffet. I'm really missing the catering. And since I am a staff like Alessandro, Riccardo, we have the opportunity to access this delightful catering half an hour before all the other people. So we have the opportunity to enter the catering in advance, and it's all for us. So that's the best thing you can do in being the staff for an event like the Italian C++ conference or the C++ Day. Well, jokes apart, I'm really missing the catering, but obviously I'm missing all the people attending. I'm missing all the people, seeing all the people face to face. So I really hope to get back to this soon. Okay, just a few information. The setup for this conference is exactly the same as C++ Day 2020. So if you really attended C++ Day 2020 last year, it's exactly the same. You don't know, you don't need to know anything more. It is exactly the same conference. But just a reminder, everything is hosted on Remo, and about this, we want to thank the Standard C++ Foundation for giving Remo to non-profit communities like us. If you prefer to stay on Remo, and this is really recommended, this is the access point to the conference. So this URL, you'll get a web page with some tabs to move across rooms, virtual rooms. So we have track A. This is the track A. If you're on Remo right now, you are on track A. Then you have track B, hosting all the sessions for track B, and then you have a dedicated page for networking that will be stay open all day long. So that's very, very easy. If you have any issues, you can reach direct links via this URL. Direct links means you have the 3 Remo events links, and also you have the list of all the live sessions scheduled on YouTube. So you have all the links to them. Uh, why I'm saying this? First of all, you can have issues. You can have technical issues. It happened in the past, so we know this can happen. Another reason is that if you are watching the sessions on Remo, you're really in the conference, meaning that if you are late for a session, the session will be late. You have no opportunities to control the video on Remo because we disable the controls. And this is to give you a bit of feeling of staying in the conference compared to C++ Day. So this is the only difference with C++ Day. On the C++ Day, you could move the video, you can move forward, you can move backward. This is not the case here. And this is really the recommended options to stay with us, really stay with us live. But in any case, if you want to watch the sessions at your own pace, don't hesitate, go to the direct links and go to YouTube. Okay, no worries about that. This is a screenshot for the C++ Day, indicating all the major points of Remo, all the important information. So the agenda is on the top right corner. You have possibilities to move across tables, all the same things as other conferences, basically. The important thing to remember is how to reach the staff. The staff is reachable searching for ++IT or staff or itCppCon on the chat. Okay, and this is the staff on Remo. Stefano, okay, I can see also Stefano here is arrived. Stefano was in the networking, so he was late because of this. He was in the networking, he was supervising and giving assistance. So Stefano and Riccardo are the guys you can reach for any problem, for any in any case, to also to flag some issues, or if you need anything. They will be on the networking all day long. Okay, basically. Well, not all day long, I think, but anyway, they will be there for the conference for sure. And this is the recommended option. If you watch the sessions, you can stay on Remo. And track A and track B host-only sessions, and this is like a virtual auditorium. Let's say you have the chat on the right tab. Ask questions only on Remo. Questions on YouTube won't be answered. That's because the conference is for people staying at the conference, so that's our choice. And you can also watch the session on YouTube in the meantime, or you can put this full screen if you prefer, if it's better for you, for your device. So no worries about that. Oh, sorry, I get back to this. Okay, the other option is going on YouTube. So if you really want to watch the sessions at your own pace, or you have issues, go to YouTube. You have the direct links in advance, so you can also add to your. You can also add reminders if you want on YouTube directly. So don't hesitate. Just another reminder, track A and track B are only for sessions. If you want to go to the networking, go to the dedicated page, to the dedicated Remo page. The networking will be open all day long. Okay, so you can go there anytime. You can go there anytime, really. That's an important information for you. A new community in Italy was recently co-founded by Stefano and Lorenzo that will be in the networking and also in live sessions today. Italian Embedded. So it's a community focused on embedded, in the embedded ecosystem, starting from Italy. And so they will have a dedicated table to speak about this community. If you feel like joining them, or if you feel like getting more information, please don't hesitate to visit their table and just to do some chat. So they will be around. If you don't find them, no worries, because they will be there. They are also watching the session, so probably they will be available for the in the networking for sure. That's a few information about some tables you should know on Remo. I realized that I omitted this information at the C++ Day. This was a bit confusing. We have a dedicated table for follow-ups after talks. So each speaker has the opportunity to stay in a dedicated table, and you can join this table for some follow-ups. You will notice these tables because they will have a title on them, the title of the talk on them, or just follow-up track A, follow-up track B. So that will be visible. Another one is a table for job opportunities. It's not managed by us. It's a table or more tables. We have one per floor. If you have any opportunity to discuss, just go to this table. My personal suggestion is just edit your profile name clearly. So make evident you are hiring. This is an example. I'm not hiring actually, but this is just an example for you. So if you state I'm hiring in your name or your title, this will be clear that you are hiring. You have opportunities to share with people. So that's my personal recommendation. This is a table you can use anyway. The other one is the silent table. There are many silent tables from the third floor, and in the networking, you can join that tables if you want to disconnect, if you want to take a break. The advantage of joining this table, instead of closing everything, you know people. You are on Remo, you are at the conference, you are connected at the conference. So you are basically expressing your intent very clearly. You are at the conference, but at the moment you cannot speak. It's like being at the phone in a physical conference, or I don't know, going to the restroom or something like that. Okay, that's exactly the same. So if you join these tables, it's not expected you want to speak. You want to stay with other people for some time. You have something else to do. Just a few conference tips. First of all, the code of conduct is the very reference point for our conferences. Please be polite and be professional. This is a professional journey. So for any issues, don't hesitate to reach the staff directly in chat, personally, no worries. Anything is fine. I recommend, after 1 year and a half being at online conferences, I really recommend to stay focused on the conference. So disable your phone notification if possible. I know it's not so easy, but try to stay focused on the conference as much as possible. And obviously enjoy meeting other people. This is the most important thing, in my opinion, both for physical conferences and for online conferences. Give feedback for us is really important. We have a single point to give feedback, italiancpp.org/feedback, and you'll get a list of surveys. We have a general survey feedback. I recommend to take this at the end. And we have one survey with 2 questions for each talk. So my recommendation here is after attending the talk, or maybe at the end, but do it, please. Give feedback also to each talk you attend. And now I have a special gift for our keynote speaker, that's Sean. You probably know that Sean's popularity increased a lot in 2013 after giving the C++ seasoning talk at Going Native with the famous quote, "That's a rotate," where he was introducing some very clever usage of rotate. And basically, he invited all of us to share our "That's a rotate" moments that I define the C++ haha moments, so the eureka moments of C++ programmers with clever usages of STL or insightful usages of some algorithms or some data structures in the standard library. So I'm resuming an hashtag that was already there on Twitter, was a kind of abandoned. So I'm resuming this hashtag. I invite you to share your own "That's a rotate" moments. So your own best haha moments relative to C++, STL anyway, insights. So that's my intention. And my personal gift to Sean is sharing what I consider the best "That's a rotate" moment for me. I had many. I was really lucky in my career at the moment because I had many of them, some of them, not many, some of them. I want to share with Sean the best one I had, in my opinion. And I blogged about this a couple of years ago. So every detail is in my blog. I don't want to steal the space, let's say, for this to Sean about this, but I just want to share 2 slides. One is my best "That's a rotate" moment is that when I realized that the maximum subarray problem that can be solved with the cadence algorithms can be written in terms of partial sum. So this is the one of the canonical forms of Cadane to solve the maximum subarray problems. I repeat, all the details are on my blog. It's a blog post of 2 years ago, so I don't want to explain this to you, but this is a canonical form. And at some point in my life, without thinking about this problem, at some point it popped out in my mind, this problem could be solved in terms of partial sum. And the final version with ranges, in my opinion, is really nice. And this is the final form of this algorithm with partial sum and with ranges. Everything is lazy. It's really nice. If you want to know more, italiancpp.org/Cadane. This is a short link pointing to my blog. And my gift for Sean is resuming this hashtag. Please make some noise on Twitter, make some noise on Facebook, on LinkedIn, share your own stories of That's a Rotate. And just an information, very quick, I shared this already on the social post and on newsletter. We have the opportunity for a discount on a great book of a friend of mine about ranges. So if you want to practice ranges, we have 25% discount on Wallet Fox book. Just a very quick information about that. We have this 20% discount. If you want to know more, italiancpp.org/ranges. This is totally, for us, it's totally open. So go to this and insert the discount code if you want this book at this price. But anyway, share your own stories of That's a Rotate. That's my gift to Sean, and also actually to the ecosystem, because we really know we are really missing some stories about that. So please share your insights with the ecosystem. Now, I think enjoy the conference, and I'm delighted to introduce you, Sean Parent. So please welcome on stage, virtually welcome on stage, Mr. Sean Parent. And let me remove this. Hi, Sean. I think good evening, maybe you from your side.
Yeah, it's almost midnight here, so
It's also midnight. Yeah.
So I'm a day before you guys.
Thanks a lot, Sean, for coming, and we are really looking forward to attending this talk. So it's really appreciated for us. Thanks a lot. I think I can leave the stage. We are perfectly on time. Well, 2 minutes late probably, but we can all leave the stage, and they are all yours, Sean. Thanks a lot for your time, and
Well, thank you very much.
enjoy the conference. Thanks a lot.
Thanks for the hashtag too.
You are welcome. Okay, I remove all.
There we go. Well, good morning, everyone. Today's talk is a warning: stood find is broken. It's a little bit of a clickbait title, but I'm hoping to convince you by the end of this talk that it's actually true. One thing to mention here, I do have a new title next to my name. I'm still a senior principal scientist at Adobe, but now instead of working directly on Photoshop, I'm restarting Adobe Software Technology Lab. And I'm pleased to let people know that Dave Abrahams is going to be joining me. So many people in the C++ community know Dave. He started BoostCon, which is now CppCon, and was very involved in the standards committee, and he's been a little out of the C++ community for a while, as he's one of the people who created Swift. So he and I are restarting Adobe Software Technology Lab. So hopefully, next year we'll have some stuff from the lab to talk about. The other thing you might notice here, if you've followed my talks, is this talk isn't one of my better code talks. I've kind of finished all the chapters as far as giving talks, not as far as writing for my better code talks. Although this talk is taken out of work that I am doing for the algorithms chapter. So that's where it kind of fits in. And I am still working on writing. And at the end of this talk, I'm hoping to give you guys one simple trick for writing better code. So let's jump in here. This going to start with a quote. This is a quote from Alex Stepanov, and I'll read it. Understanding why software fails is important, but the real challenge is understanding why software works. Context for this quote is years ago, I worked at Apple, and when I first joined Apple, I was assigned a bug to fix, and it was a fairly nasty bug and took me a while to figure out. And I fixed it and took it to my mentor, who was somebody named Darren Adler. And he said, "Well, that's great, good job, glad you found it, glad you fixed it." And then he asked, "How can we prevent others from making the same mistake?" And that one question kind of set my career in a bit of a different direction. And I spent a lot of time focusing on understanding why software fails and how you avoid having software fail. And so I told this story to Alex, and he listened. And this was his response, that understanding why software fails is important, but the real challenge is understanding why software works. And hopefully by the end of this talk, you'll understand how profound of a statement that is. So let's go back a little bit in time. This is a paper from Bob Floyd, written in 1967, Assigning Meanings to Programs. That's a picture of Bob. This is an early paper that starts to talk about how we can reason about software and about software correctness. Bob Floyd is a Turing Award winner. He was a college professor and supervised 7 PhD graduates. One of his graduates was an individual named Jim King, who I had the pleasure of working with for many years at Adobe. Now I really wish that I had actually found an excuse to author a paper with Jim, just so I could be, one removed from Bob Floyd. Another one of his students was Bob Tarjan, who's another Turing Award winner. So, being a Turing Award winner and having taught a Turing Award winner is quite the accomplishment. But Bob's work on assigning meaning to programs was picked up by Tony Hoare. And this is a paper from 1969 from Tony Hoare. That's a picture of Sir Tony Hoare. And this is called an axiomatic basis for computer programming. And this is a formalization of the work that Bob had started as far as ascribing meaning to software. So he developed something that's now known as Hoare logic, or it's also referred to as Floyd-Hoare logic. And Floyd-Hoare logic describes computational statements as a Hoare triple. A Hoare triple looks like this. You've got P, Q, R, where P is a precondition, Q is an operation, and R is the postcondition of the operation. Statements are combined with rules for assignment, consequence, composition, and iteration. There are specific rules spelled out in the paper for how these assertions are combined. And so given a sequence of statements and assuming some initial set of preconditions, you can show that the subsequent postcondition if you can show that subsequent postconditions guarantee subsequent preconditions are satisfied, then the program is correct. Right. So let's take a little bit of a look at this. These are the properties of addition for integers. Right? For all a, b, and c, a plus b plus c is equal to a plus b plus c. It's associative. A plus b is equal to b plus a. It's commutative. A plus 0 is equal to a. There's an additive identity. And a plus negative a is equal to 0. There's an additive inverse. Right? But when signed integers overflow and underflow, the result is undefined. Right? Int is not the same as the set of integers. So in Hoare logic, this would be expressed as an additional axiom. We're just going to deal with overflow here, not worrying about underflow. But what this statement says is there does not exist an element x, which is within the set of integers, such that x is greater than the maximum value. From that, we get a Hoare triple for addition that would look something like this. A plus b has to be less than or equal to max, and then we can do a plus b and assign that to n. And the post condition then is n is less than or equal to max. Okay, so we can do this. It's quite cumbersome to reason about a piece of code this way. And even Tony Hoare recognized in his initial paper, he hadn't completed the characterization of integer arithmetic. And it is quite complex, and there was a lot left to be done there. Nevertheless, this paper serves as the foundation for formal methods and pretty much everything that has to do with formal methods these days. You can see this in tools like the Clang Static Analyzer. This is the result of running the Clang Static Analyzer on a small but bad piece of code within Xcode. I just took a screenshot here, and you can see at the end of this, what we see is undefined or garbage value returned to the caller as step 6. That happens as we return star next p. The full thing that the Clang Static Analyzer is looking at is it says, well, I have this array A that only has a single element. I call get next integer, passing it A, right? So that's step 1. That leads to step 2, where we've entered get next integer from main. Going to step 3, we call next. Inside of next 3, which I couldn't capture with one screenshot, is step 4, where we increment our pointer, and return the successor of p, and dereferencing that successor, returning it from our function, is going to end up returning the value 1 off the end of the array, which is a garbage value to the caller. Right. So this is all built up by looking at the code a statement at a time, understanding what the axioms are around that statement for the preconditions and postconditions, connecting those together to build a increasingly complex model, looking actually through functions, from main into get next int into next to build up those models, and then determining that this piece of code is incorrect. So the next important piece of work in our story here is design by contract. This is the earliest paper that I could actually find a copy of for design by contract. The first reference to a paper is from 1986. This paper is from 1992, so a few years later. And design by contract is the work of Bertrand Myers, who wrote the Eiffel programming language. Right. And design by contract takes some of the ideas from Tony Hoare and raises them into the interface for classes and functions. So in Eiffel, you would have preconditions and postconditions asserted in the interface for code. So this is a method on a class, set seconds, and it has a precondition named valid arguments for second, and it requires that s, which is our argument for second, is in the range of 0 to 59. Okay, and then we've got a post condition, which is the ensure statement here, that our member second, that's going to be a member of this class that this is a method on, is equal to s. Right. The other thing that design by contract introduced was class invariance. So here we have a class invariant. The class invariant is named second valid, and it basically says that our member second is within the range of 0 to 59. Right. So a class invariant serves as a postcondition for all the public operations on a class. And by extension, class invariants define a precondition for any operation taking an instance of the class as an argument. Now, there are some limitations to design by contract. Assertions must be expressible in code. Complexity of assertions is limited, meaning if you have a linear time assertion on a constant operation, that can transform code from being ON to ON times M, and that can mean that it's not feasible to test that piece of code. You cannot express universal quantifiers, such as for all or existential quantifiers. There exists. But there are some key contributions that came in with design by contract. It simplifies formal methods by inverting the process to be top-down. So you're starting by giving a precondition to a function, and then the operation becomes to prove that that function satisfies the postconditions. That's much easier to do than to just look at the individual statements and derive what the precondition for a sequence of operations are and what the postconditions are for that sequence of operations. Right, so this makes formal methods practical for every programmer and lifts it outside of just the tooling domain. But in steps a villain here. Hiram Wright is going to play our villain. This is a statement of Hiram's Law. The term Hiram's Law was coined by Titus Winters. With a sufficient number of users of an API, it does not matter what you promise in the contract. The contract here is Bertrand's design by contract. All observable behaviors of your system will be depended on by somebody. So even though Hiram himself doesn't go around violating contracts, he makes a good villain. So let's take a look at how this happens in real code. We're going to write a piece of code to remove the first odd number from a vector. So we've got a vector 0, 1, 2, 3, 4, 5. We want to remove the first odd number. In this case, we want to remove the number 1 from our vector. So we're going to reach into our toolbox of STL algorithms, and we're going to write this piece of code that says remove if from begin to end, and then we've got this lambda expression that we're passing in as our predicate. And our lambda here has state, which is why we made it mutable. So our state is initialized to 0, and what we're going to say is if the argument that passed in is odd and n was equal to 0, and then we're going to increment n so it won't be equal to 0 anymore, then this will return true. Otherwise, it's going to return false. So it's only going to return true on the first odd number. Now, after we do that, we actually want to trim off the end of our vector. So we'll pass the position returned to erase, and we'll erase from p to end, and then just display our vector. When we execute this piece of code, here's what we're going to see. Maybe. Right? It removed 1, but it also removed 3. We lost the first 2 odd values, but not 5. But if we run it under a different standard library implementation, we actually might get the right answer. And if the first time we ran it, we might get the right answer, we might never even know that our code was wrong. So what's the problem? Well, this is a legitimate implementation of remove if, and this is pretty much what you'll find in many of the standard libraries. So remove if starts with a call to find if, and that call to find if is finding the first instance that satisfies the predicate. In this case, our predicate is trying to find the first odd number, but our predicate is passed in by copy. And so at this point, our n is equal to 0. we pass it into find if n is equal to 0. We find the first item we're going to remove, and then we start the loop to remove the remaining items, and we're running with the original copy of the predicate, so n is now 0 again, and we're going to remove a second copy. Right. So if we understand that, we can fix our piece of code. So this is our second attempt. We've got our vector 0, 1, 2, 3, 4, 5. And now we have almost an identical piece of code, but we lifted n out of the lambda, so our lambda no longer has to be mutable. And we put it up here, and we just pass it in by reference. So now any copies of this lambda that get made inside of remove if are going to share the same value of n. So we execute this piece of code, and it'll work. And you can load this up in Compiler Explorer and try it with all the common implementations of compilers in the standard library out there, and you'll find that it works on all of them. But is it correct? Well, it turns out it's not correct. The standard says about the predicate that we pass in to remove if, that given a GL value u, so some value of type u, possibly const, some value u, possibly const of type t, that designates the same object as star first, where star first is just some iterator. Predicate u shall be a valid expression that is equal to predicate star first. Or put another way, our predicate is required to be a regular function. A regular function is a function where, given the same argument, it always returns the same result. The predicate that we're passing in to our remove if statement violates that requirement. So technically, that prior piece of code, even though it works on all the compilers, is undefined behavior. Right? We just ran into Hiram's law. And I can guarantee you that there's code out in the wild that plays similar games with the predicate passed in to remove if and other standard library functions. What's going on here is what's called an unnecessary precondition. Right? We've got a difference between what we have with Bob and Tony's definition of how we reason about code correctness by looking at individual statements and deriving what is correct and what is allowed, and programming by contract, where we're making an assertion up front on a set of preconditions and postconditions. Those preconditions in design by contract can include preconditions that are not imposed by the implementation, maybe not by any implementation. That's called an unnecessary precondition. Right? Now, if we have no preconditions, that would be expressed as true QR. And typically, not stating a precondition assumes no precondition, that you can pass in anything. So, except for those preconditions that are imposed by strong conventions. Now, there are operations without preconditions. So a question here, are operations without preconditions or weakest preconditions good? Right? When we're writing a piece of code, should we try to minimize the preconditions that we have on a piece of code? Should we try to eliminate unnecessary preconditions? Converse of that is, are unnecessary preconditions bad? To quote Kate Gregory, it's complicated. To illustrate, let's take a look at signed versus unsigned integral types. Signed integral types in C++ have more preconditions, stronger preconditions than unsigned types. Right? It's undefined behavior to overflow or underflow a signed integral type. Unsigned types, on the other hand, are modular, do modular arithmetic, mod 2b, where b is the number of bits within the unsigned type. Unsigned type arithmetic still has preconditions. For example, if I wrote this piece of code, unsigned a, and then I add a to the value of 1, that's undefined behavior. It's undefined behavior to read from an uninitialized variable. So one of the preconditions of addition for an unsigned type is that the object has to have been initialized. A precondition of reading a variable is that it has been initialized, which is what I just said. Now, I actually looked. I'm not aware of any operation in C++ without some form of a precondition. There's nothing that's just true as a precondition. If somebody can find an example, I'd be interested. So let's take a look at an algorithm using signed integers, just so we can contrast this with what we can do with unsigned integers. This algorithm is a classic graphics algorithm for drawing lines called Bresenham's line algorithm. The algorithm was originally developed to plot lines on a plotter by minimizing the distance that the plotter can do. Plotter has a particular resolution, it's running with stepper motors, so to minimize the difference that the pen is ever from your idealized line. Now, that algorithm got translated into, it was originally a floating point, got translated into integer arithmetic, and I actually don't think it's the same algorithm that's described in the Bresenham paper, and at some point I might actually write a paper on that. But nevertheless, this has become known as the Bresenham line algorithm, and this is what you'll typically find in a graphics textbook. So let's take a little bit of a look at this algorithm. We're only dealing with lines in the first to 1/8 coordinate of our system. And so this is just looking at the internal guts of the Bresenham line algorithm. So coming in as arguments, we're not taking points, we're taking our delta x and delta y, right? So a slope of a line dy over x. And then taking some function out, which we're going to call with a point, an xy point, plotting the line starting at 0, 0, that follows it up through delta x over delta y positions. We'll get to the assertion in just a moment, but so we're just going to loop with x going from 0. Well, x does not equal our distance x, and increment x at each level. We're going to initialize y at 0. We'll see where y gets incremented in a moment. And then we have this variable a, which is usually referred to as an accumulator. A is initialized with dy over 2. The reason for that over 2 is because we're starting in the middle of a pixel. If you don't do this, your lines look a little skewed off center. So we start at dy over 2. So we always output the first point to start, which is going to be 0, 0. Then to our accumulator, we add dy. Okay, and if now our accumulator exceeds dx, then we're going to increment y, and then we're going to subtract dx from a, and we're going to keep looping. Okay, so that's the Bresenham line algorithm. Now, sometimes if you look this up, like I think on Wikipedia, you'll find small variants of this. Since dy over 2 is trying to get the halfway point of a pixel, but this is integer arithmetic, sometimes people will always double dy and dx coming into the algorithm, and then just use the original value of dy here so that we always get an exact value for our midpoint, but the basic algorithm is going to be the same. So let's write a little piece of code to exercise that. We're just going to ignore x since we know that it's getting incremented, and we're just going to plot out some asterisks based on the value of y. And so if we ran this piece of code, we'll get that. And what you're seeing here is the 6 is our dy, so our orientation is flipped here. Our y is actually going left to right, but you'll see that this is exactly 6 asterisks wide, and our dx is 10, and this is 10 asterisks tall on the whole thing. And you'll see we get this nice even stair step, at least as even as we can get for a line at that angle. Now, let's drill in to this algorithm just a little bit more. Let's just look at what's happening with this accumulator A. Right? We're adding dy, we're checking to see if we've exceeded dx, and then we're subtracting off dx. What those statements are doing is modular arithmetic, right? We're saying a plus dy assigning into a mod dx. That's what those 3 statements do. Now, if we were doing this in unsigned integer, we could get modular arithmetic for free, right? In C++, unsigned arithmetic is mod 2n, right? Which could also be stated as mod the maximum value for our unsigned int plus 1. So all we need to do is project our slope to a dx prime of max plus 1, right? That's a simple cross multiply. We have dy over dx is equal to some dy prime over max plus 1. Solve for dy prime. That's max plus 1 times dy over dx. And that gives us a fast Bresenham line algorithm. All right, so let's take a look at what's going on here. We'll handle the assert last. That's our precondition. But coming in here, we have, this is our dy prime, is exactly what I said. It's uint max plus 1. The reason why this works is because that 1 is a double. So this is going to convert our uint max to a double. So we're not overflowing or wrapping. We're doing this now as arithmetic on a double. Times dy also as a double, divided by dx as a double again, and then truncating the result back in to dy. So we're going to lose a little precision there, but it's less than a pixel across the entire coordinate space for an unsigned value. So we're fine here. Okay. The structure of our loop here is exactly the same. We're going to output x and y, but now our modular arithmetic is just this one line, a plus equals dy. And we can increment y every time we wrap around, which will be anytime a is less than dy, right? Overflowing is defined behavior. If you run this through Godbolt, what you'll find is these 2 statements just turn into 2 instructions. The first one is an add, and the second one is add with carry with a constant 0. So the compilers recognize that this condition can only be true when that overflows, and that's what the carry bit is in most processors. Okay, so the result here now is an algorithm that's about 15% faster, just as is, but it's also much simpler to vectorize, and you can get significant performance gains out of vectorizing this. This algorithm is actually used in Photoshop for the iPad. I worked on this with Nick DeMarco at Adobe, and I'm going to leave you guys something to ponder, which is we implemented this. It's used for drawing, but it's actually not used for drawing lines. So I'm going to let you guys ponder what else you could draw with Bresenham's line algorithm besides lines. Now, this brings us to our assert. You can see our preconditions were greatly reduced. We don't have to worry about being greater than 0 because that's imposed by this being unsigned. We don't have to worry about the overflow case because that's the whole point, is that we're wrapping around using modular arithmetic. But our middle assertion here before was that dy was less than or equal to dx. We can't quite do that anymore, because if dy is equal to dx, we can't distinguish that with modular arithmetic between dy being equal to dx and dy being equal to 0, right? Right. Dx mod dx is 0 in modular arithmetic. So this is a little bit different algorithm in that now if we wanted to draw a line at 45 degrees, we have to special case it. This piece of code won't handle a 45-degree line, right? It also won't handle a line of 0 length, which would also be 45 degrees, right? Because dx can't be 0, and that's also imposed here by our division. But if we run this piece of code, we would get exactly the same line. Now, we won't get exactly the same line in all cases because this is an approximate to the previous Bresenham line algorithm, but it's a good approximation. So unsigned versus signed integers. What are the trade-offs here? Well, with unsigned integers, it's easier to detect overflow with the modular arithmetic. We can exploit modular arithmetic properties, right? But usually when we're dealing with math within software, we're not dealing with modular arithmetic. We're dealing with a subset of integers or a subset of natural numbers. And signed math provides more opportunities for analyzers to detect possible overflows if we forget to assert them. Signed math also provides more opportunities for compilers to optimize assuming no overflow, right? If overflowing is undefined behavior, a compiler can assume it's never going to happen. If we take the assert out of the original Bresenham algorithm that we showed and pass it values that would overflow, then UBSAN will actually pick that up for us and let us know that our software has a bug. Right? Now, I kind of wish that we could mix these two. One possible solution would be adding type attributes to the C++ integer types so that I could write something like this. I could specify that I've got an unsigned integer with limits between 0 and 59. So with this, my tools could detect to give me an error if I exceeded those limits, and my compiler could optimize assuming that I never do. So unnecessary preconditions, right? Having additional preconditions, they provide flexibility of implementation. They can ascribe meaning and intent to an operation to say that I'm not intending this thing to overflow, for example. They simplify the requirements and reasoning about a piece of code. But at the same time, they limit clever uses that exploit defined behavior. They allow for variance in behavior between implementations. And they open the door to run afoul of Hiram's law. So it's not simple. Despite all this, somehow within the C++ community, there's become a debate over which is better, unsigned versus signed values. I'm strongly in the unsigned camp, and here's the quote to support it. God created the natural numbers, and all else is the work of man. So use unsigned variables. But we're getting a little ahead of ourselves. We haven't talked about ascribing meaning to generic code. So let's talk a little bit about that. The idea of generic programming was first published in 1989 by these two people, Dave Messer and Alex Stepanoff. Right. In an important paper in 1992, the ideas of generic programming were refined, and this paper introduced the term concepts. Right. This was done by James Dennert and Alex Stepanoff. Here was what that paper said to introduce the term concepts. We call the set of axioms satisfied by a data type and a set of operations on it a concept. What concepts do is they associate semantics and complexity, right, complexity of an operation, with syntax. Right? The complexity is important to the meaning of our software. Right? The only difference between the iterator categories, the only difference between a forward iterator, a bidirectional iterator, and a random access iterator fundamentally is the complexity of the operations. Right? Concepts define a component that will work on any type satisfying the requirements. So they define a component being an algorithm or a container that will work given anything passed in that satisfies the requirements. So if I want to sort, I can sort things so long as my range satisfies the requirements of a range and my value satisfies the requirement for a strict weak ordering, right? So as such, concepts assign meaning to an unbounded set of operations, right? Stood sort lets me sort an unbounded set of things, set of types. So an argument to a component is required to satisfy a concept. And a data type or operation may guarantee that it is able to satisfy a concept. That's a particular data type. Oh. So this is important. This lets us plug in things like, can I sort a vector of integers? Can I sort a vector of strings? Right? We can now mix and match those operations and containers. So a requirement applies to the arguments of a type or operation and consists of required valid expressions, preconditions, and the semantics of those expressions. A guarantee applies to an instance of an object. Asserting such an instance satisfies a requirement or models a concept. Right? Those are saying the same thing. Satisfying the requirement is modeling a concept. So let's take a look at a very simple algorithm, distance FL. Right? Stood at distance is just going to return the distance between a pair of iterators. It requires that F and L satisfy input iterators. Input iterators requires that you've got a pre-increment, a post-increment, and a post-increment and dereference expressions. Those are all valid expressions. And all of those have a precondition that our iterator I does not equal L. Further, F and L satisfy a trivial iterator because an input iterator has to satisfy a trivial iterator. A trivial iterator has to be assignable, equality comparable, and default constructible. Equality comparable has a precondition that the arguments are in the domain of equality. And distance has an additional precondition that FL is a valid range, right? And what we mean by a valid range is that either F is equal to L, or if I increment F, I will eventually end up with F equal to L. So naming the set of requirements is a significant simplification. This is one of the huge contributions that concepts bring to our ability to reason about software. Right? The concept stood input iterator encapsulates a fairly complex set of syntactic and semantic requirements. Only the syntactic requirements are enforced by the compiler, but analyzers and sanitizers can validate some of the semantic requirements. Concepts in the standard are requirements of the arguments to the library components. They're not requirements of the implementation of the standard types. Although frequently the standard types are described as guaranteeing they satisfy those requirements. The distinction and the use of the term requirements in the standard causes a lot of confusion. Sometimes even people on the standards committee read the requirements as this is what an implementer must do. That's not the point. It's this is what the user must satisfy to use their types with the standard components. So named requirements or concepts are distilled from a set of related components, such as algorithms or containers, a set of common models, right? A stream is an input iterator, right? A iterator into a vector or an iterator into a deck are random access iterators. An iterator into a list is a bidirectional iterator. Those are models of iterators. Okay. They create a simple way to match data types to components and know that the resulting piece of code will work correctly. But for any specific component, some of the requirements may be unnecessary. If we just looked at our distance there, the distance between two iterators, distance requires an input iterator, and an input iterator is required to be dereferenceable, but distance never dereferences the iterators. That's just an unnecessary requirement that's been imposed on there. Okay. The purpose is not to specify the implementation of the algorithm, but to specify the meaning of the algorithms, right? Or the containers or the components where these are used. So with all of that in mind, let's get to the point of our talk here, stood find. Right? So what does find do? Well, conceptually, it finds the first elements in a sequence, first to last, that's equal to value that's passed in. Well, what does it mean for two things to be equal? Two objects are equal if and only if they represent the same entity, i.e. they have the same value. From that, we can derive the properties of equality. Equality is an equivalence relation. An equivalence relation says for all A is equal to A. It's reflexive. For all A and B, A equal to B, if and only if B is equal to A. It's symmetric. And for all A, B, C, A equals to B and B equals to C implies A equals to C, A equals C. It's transitive. Equality is also consistent with other operations on a type. Right? If we copy a type, copies are equal. That's the definition of copy. If our type is totally ordered, if it's less than comparable, then we have an excluded middle. So if A is not less than B and B is not less than A, then that implies A is equal to B. Right. So let's look at the old specification from the old SGI STL. This is not the original STL, but pretty close to it. STL was originally developed at HP, came out at HP Report, and then Alex went to work at SGI, and a very common early, or very popular early implementation of STL was the SGI STL. The docs are still available on boost.org, which is where I found this information, and it's largely this documentation that was included in the early versions of the standard, where C++ was first adopted, or where STL was first adopted. So here's our signature of find, and we see up here we're using the names of our arguments as the names of concepts. At this time, they were just called named requirements. So find takes a pair of input iterators, and it takes an equality comparable value. Equality comparable, meaning the type, is a model of the equality comparable concept. Input iterators are a model of input iterators, and equality is defined between objects of type equality comparable, meaning our value, and objects of the input iterator's value type. So when we dereference our input iterators, we get something that's equality comparable with our value. We have precondition that first last is a valid range, and our complexity here is linear. Now, the definition of equality comparable from the old documents looked like this. Right? We have an expression x equals y, which is called equality. It's got the precondition that x and y are in the domain of equality. And then here it's got our basic properties of an equivalence relationship. They did add one more here for the identity, which is just saying that if it's exactly the same object, then those objects are equal. It's also reflexive, it's symmetric, and it's transitive. Now this is the definition from C++20, also C++17, and I didn't trace back how far this actually goes. This is the definition of find. So we still have our input iterators here, and there's overarching requirements around the iterators and the first last forms a valid range. Okay. Now we say let E be star I equals value for find, meaning for this instance of find that we're documenting. This function returns the first iterator I in the range first last for which E is true. It returns last if no such iterator is found. That's it. This definition of find doesn't mention equality comparable at all. Now the standard still contains wording defining what equality comparable is. Right, now these are some of the legacy requirements. So this is C++17 equality comparable. There is a stood equality comparable, which is defined similarly as a concept. But this is the older definition. Okay, and we see we've got the expression A equals B. It's got to be convertible to bool. And then again, we've got our requirements that fall into the same basic pattern. For all A, it's reflexive. Okay. If A equals B, then B equals A, and it's transitive at the end here. So let's take a look at why this is problematic. We're going to use nan as a placeholder for a value which is not equality comparable. A refresher on nan, right? Nan is a floating point type. In this case, just nan generates a double. It's typically generated by 0 divided by 0. Nan equal nan is false, meaning nan is irreflexive. So nan does not satisfy the requirements of either equality comparable or CPP17 equality comparable. So let's write a piece of code doing find. We've got an array A of doubles. And we're going to try to find nan within that array. What does this return? Right? We'll print out the result. This, of course, is going to return not found. Even though I'm trying to find nan here, and nan exists, I didn't find it. Now in the old SGI, STL, this would actually be undefined behavior. We don't satisfy the requirements. NAND does not satisfy the requirements of a quality comparable. But in the new definition of find, this executes, it just doesn't find anything. So let's take a look at another example. Start with the same array, but this time we're just going to try to find 3. And same piece of code to output our result. And hey, look, we found 3. But did it work? Well, what if we stated the problem this way? Given a sequence of fractions, a over b, find the first fraction such that a equals xb. And we gave it this. We said x equal to 3. Oops. And what's going to happen? That's going to find this value. But this one, the NAND, is actually the first instance that satisfies our problem. The problem here in math is comparison with an undefined value is undefined, but our floating point types don't have a good way to represent that. So we just return false. So even though this code executes and it returns a value, it's not necessarily the correct value. The change is even a little more subtle. If std find if the requirements for it were restated to require CPP17 equality comparable, the following code would be undefined behavior. This piece of code would be undefined behavior. Just trying to find the value 3 in an array of doubles absent any NANDs. But the above piece of code is well defined with the SGI definition of a quality comparable. How can that be? Let's take a look back at SGI STL equality comparable documentation. There's this precondition. X and Y are in the domain of equal equal. That precondition is missing from the CPP17 equality comparable requirements. And there's no overarching requirement that I can find that adds that back in. This is a problem. The term the domain of equal equal, or the domain of an operation, was fairly ubiquitous in the original documentation for STL. The term domain of the operation is used in the ordinary mathematical sense to denote the set of values over which an operation is required to be defined. This set can change over time. Each component may place additional requirements on the domain of an operation. These requirements can be inferred from the uses that a component makes of the operation and are generally constrained to those values accessible through the operation's arguments. This is what's meant by the domain of equal equal, and the precondition, the domain of equal equal. So what does this bunch of verbiage say? Right? It means the domain of an operation is not the types of the arguments. For a type T to satisfy some requirement P, such as for all A through some set of values, P on those set of values. If we've got a requirement like that, T must guarantee that there exists a set of values within T such that P is satisfied, right? It's not that every value within T has to guarantee that. There only has to exist a set of values that guarantee that. So double and float satisfy the notion of equality comparable, where they don't actually satisfy the notion of CPP17 equality comparable, so long as nan is not in the set being compared. Right? The absence of nan in the sequence for find is a precondition, and that's been lost. So std find doesn't require that there exists any equality comparable values in T at all. std find doesn't guarantee that it finds value, even if value exists in the sequence. The meaning of std find is reduced to it works as implemented. Fortunately, it's trivial to show that if and only if operator equal equal models equality comparable, and all the values in the sequence and the value being sought are in the domain of equal equal, then std find will actually find. So let's go back to where we started. Understanding why software fails is important, but the real challenge is understanding why software works. A lot of times we're faced with this. We have a little bit of correct code, we have a lot of buggy code, and we're trying to avoid failures. But in avoiding failure, what we do is we weaken requirements. And that doesn't actually add to our correct code. It just adds to a pile of code that happens to work. It isn't correct, but it doesn't fail hard. This is a quote from Titus Winters. I work with very good programmers, and I see a ton of happens to work, and very little actually correct. So what can you do? Well, after trial and error, and after searching on Stack Overflow, and after Googling, maybe you have code that happens to work. Take the time to read the specification. Look up anything you aren't clear about. Ask specific questions of experts. Clever uses require additional validation. Right? If you go back and you look at our clever use to remove the first odd value using remove if, that's a clever use of the algorithm. That requires additional validation. The more clever, the more research you should do. Is the code correct or not? Think about the meaning, the semantics of your code, right? What's your code supposed to mean? Ensure your use reflects the implied semantics, right? Are you using find to actually find something, or are you using find to do something else? Don't use find to do something else. Ensure your names reflect the semantics of what they represent. So be careful when you're naming functions. A usual example of this is don't name operations that aren't constant time with a noun. Use a verb, right? Requires some action. Go search. So here's my quote to take away. The gap between code that fails and code that is correct is vast. Within that gap lies all the code that happens to work. It's most of our systems. Instead of trying to avoid code that fails, strive to write code that is correct. And if you do that, you'll write better code. So thank you for coming to my talk today. I still have some time, so I'd like to see if there's any questions or comments coming in. Maybe one of the administrators can help me. Maybe I'm not looking in the right place because right now I'm just seeing an empty chat.
Here I am, Sean. Thanks a lot for the session. Well, we have a few questions in Remo, and the first one is I'll show it in on the talk itself. The first one is does equality comparable semantically allow comparing standard string and string view? Should it? I think you can read the question on StreamYard as well here on the screen.
Yeah, so yes, it should, in the sense that well, it does, and it should in the sense that string view can represent the same value. In the old original SGI-STL, Alex was very strongly against comparisons of mixed types. He wouldn't even want you to compare a string to a car star. It was actually, we had a long debate on this topic at the Palo Alto meeting, which was a meeting where the idea for concepts light kind of came out of. It was a meeting to reconcile concepts. And the thinking there changed to say, no, really equality comparable is defined by do these things represent the same value? Do they represent the same entity? And so as long as your string view and your string conceptually represent the same, could conceptually represent the same entity, then they should be equality comparable.
All right. Thanks. And okay, we have another one. Let me check the ranking. The ranking is this one. Okay. Okay, this one. The name axiom in the definitions of a concept implies conditions that need not or perhaps cannot be checked, proved. What's your take on checking those axioms?
Yeah, it's absolutely true. I mean, an axiom like there exists possibly cannot be proven. This goes back to what I was saying about Bertrand Meyer's fundamental contribution here, which is inverting the system. It's easier to kind of lift the axioms outside to the interface, state them, and make it a requirement that the caller prove them. And that doesn't necessarily mean that the machine can then come along and prove them. That's up to you as the developer. Just even something simple like if I had a very a large sequence, I would have to scan the entire sequence just to check that there were no nans in there. But worse, if I didn't know that I was looking for a nan, if I was looking for any value within my sequence which was not equality comparable, to check that I would have to compare every value within the sequence with every other value plus with my value, and that would not be tractable. But looking at it from outside the system, it typically is pretty easy to prove that, yes, I can compare all of my strings, or I can compare all of my doubles so long as there's not a nan in there, and satisfy that requirement.
Well, thanks.
Yep.
And okay, we have another one from Nico. That is not Nico Iusuttis, it's Nico Liberato Candio, and is this one. Okay, is standard count falls in the same pitfalls when it comes to equality? And what about standard countif? Is your concept extendable to other algorithms?
I haven't looked through how all the algorithms are defined. This talk actually came out of a long-standing complaint that I've had about how the requirements for moved from objects are stated, which is that the requirements are stated as being valid but unspecified. Now that's been weakened to just stating unspecified. The reason for that is there was no definition of what valid meant. As I said, there aren't really any operations that have absolutely no preconditions. So saying that you have an unspecified value doesn't tell you anything about what you can do with it. And the root of that problem is the removal of this notion of the domain of the operation. And the fix that I've proposed, there's a paper out there now, it's P2345 if you want to look it up, been submitted for the standard. The fix for that is to reintroduce the name, the domain of an operation as a general term that applies to all operations within the standard, using the wording almost exactly what I had on the slide here previously, and then specify exactly for a move from objects what operations that move from objects has to be in the domain of. So that's my fix to that problem. Unfortunately, in something like find, when you're trying to change the requirements within the standard, it's a breaking change if you strengthen the requirements. You can only weaken the requirements. And right now, the requirements of std find have been weakened to the point that it's worked as implemented. They really can't get any weaker. And we can't go back and add the requirement that std find value has to be equality comparable. So it becomes the somewhat permanent wart, right? The degrees of freedom that you have within the standard without making a breaking change that would require versioning or a rename of some point of some kind to avoid breaking code, is that you can weaken requirements or you can strengthen guarantees, right? But you can't go the other direction.
Yeah, the backwards compatibility is always one of the most important things we have in C++. So we really care about it. So yeah, I understand.
Yeah.
I see the point. I see the point.
Yeah, and one of the problems with named concepts becoming part of the language is that a concept now serves as both a requirement and as a guarantee, which means you have zero accesses of freedom for the named requirements within the standard, which means that if you get one wrong, you have to come up with a new concept. You
A new
can't
concept,
just,
yeah.
yeah.
Yeah, I see. Yeah. Okay, we have another one about sorted ranges, and is this one. So you think there is room for having a concept of sort of sorted range? This way, standard find can run in sublinear time, so the implementers are free to do some optimizations behind the scenes.
Yeah. Really sorted is a precondition, right? And that it doesn't require any additional semantics of the values. It's simply how the values are structured, and so it's a precondition, and we somewhat have that, right? Finding in a sorted range, you would typically call lower bound would be your which will do a binary search to find within the sorted range. Now, in the context of the range library, maybe, I haven't given that much thought. Eric Niebler might have. If you want some way to specify that a range guarantees that it is sorted. as a single entity? Maybe.
Maybe yes. Yeah. Well, it could be useful any way, but yeah, it's something to
Yeah.
be proposed very cleverly. Yeah, I see. I
Yeah.
see the point. I see the point. And okay, we have another one from Victor. Victor is this one. Yeah. So, do you think that usage of optionals in containers complicates requirements on guarantees or of algorithms?
No, not really. I mean, in some sense, like if I used, an optional float instead of a nan, um, my code would have actually worked because, optionals, basically an empty optional is equal to an empty optional, as opposed to not being to run into the problem of nans. And so optionals are equality comparable. Um, so no, I don't think that optionals add any particular complications to things.
All right. Okay, we have another one from John. Okay, from John is this one. So it's a long one. You said that correcting the requirements of for find would be a breaking change. The committee has accepted breaking changes when the argument be made that the broken code was already. Sorry, it was continuing to another
Yeah.
one. What would the practical impact of correcting the requirement? What would break? Let me edit. Oh, this is the okay, because we have a limitation of size. That's an edge case. It wasn't tested, so that's
Yeah.
nice.
That's fine.
Yeah, this one. What would be the practical impact of correcting the requirement? What would break?
Well, the code that I put up there that was, if you had code that was trying to find a nan or code that was even trying to find 3 in a sequence of nans, that code would become undefined behavior. Um, so you'd be moving potentially code from defined behavior to undefined behavior. Um, uh, uh, I would almost bet that someplace somebody's doing find on a sequence that does have a nan in there and just skipping over it. I myself have used nans as placeholders, because optionals are a little heavyweight. So maybe I've got a sparse array, and so I'll fill in the unfilled in sections, initialize them with nans to distinguish them from other values. And nans can even carry a payload, so you can have a 1 nan and a 2 nan and a 3 nan. So you can have different values of nans within floating point values. Um, I don't think I've ever called find on such a thing, nor do I think I would, but I could imagine somebody out there who does, or just somebody who did accidentally, and now you're shifting their code, which has defined behavior, even if it's questionable behavior as to what the meaning of it is, that suddenly moves into undefined behavior. So would it have a
So,
huge impact? Probably not. If we did it across the entire library for everything that was broken, it would probably have a pretty significant impact.
so John was commenting that that code was broken already.
Yeah.
So yeah. Okay, we have another one from Francesco. Francesco is asking if could no, sorry, we have one from Eduardo actually, because we have we have the ranking of the most voted questions. So I'm sorry, Francesco. Just 1 minute. Eduardo is asking if this is something else. It's another topic. It's about epochs. The proposal from Vittorio.
Yeah.
Could introduction of epochs you think can help fixing the future C++ versions? So this kind of problems, backwards compatibility issues. What's your thoughts?
Yeah. I'm somebody who's strongly in favor of versioning and of some kind. I haven't looked at haven't looked in detail at the specific EPEX proposal, but I do think that it's somewhat ridiculous that we have things within the standard that we know are broken and we know what the fixes are, but we don't want to do something that's, just a base rename like we did with threads, where we now have JThreads and threads. We haven't wanted to do, an std2 or an inline namespace for a v2, or any of the previous things that have been tossed out for ways to version things. But I do think that we do need a way to version things within the language, and both to clean out some of the older cruft, and to move things forward. As somebody who, I was a little surprised that like a bunch of the old binary predicate and unary predicate that were removed in C++20 broke a bunch of my code, and I thought, I wish we just had versioning, because they weren't doing any damage to my code. Those were things that were removed from the language, I think, unnecessarily. It's like, yes, they're no longer needed and they're not recommended anymore, but they were just kind of dead weight at this point. So I think some form of versioning or EPEX would be a better way to solve that.
Yeah. Great. Yeah, we look forward for this promising concept in the future. Vittorio will defend it probably at next meetings.
Yay.
And okay, we have another one from Francesco, finally. This one is your thought about could concepts avoid defining APIs that can be improperly used? Do you think that C++ shall support also mechanisms to enforce preconditions and postconditions at runtime?
So, well, so two questions.
I think it's
there,
about contracts, probably. It's kind of about
So
contracts.
the second one's about contracts.
Yeah, the second one. Yeah.
Right. So the first one, concepts certainly help us for a couple reasons. One is the standard concepts come with defined semantics, which then, I could see things like the Clang static analyzer and the sanitizers could now incorporate those semantics in their building models and actually check code. Beyond just checking the syntax, which is what the compiler's doing. And there's if you look at the actual concepts, we kind of have placeholders in the concepts for semantic requirements that have no syntactic representation, which is true of a couple of the concepts. And so those placeholders are basically just there to help tooling. Can they avoid it completely? No, nothing can avoid it completely, right? They can make it better. Would contracts help? Yes, I think contracts would help. I'm hoping that the contract proposal, since there was a contract proposal that got cut pretty late from C++20, and I thought that it was not fully fleshed out. So I thought cutting it was a good thing, and I'm hoping that the time that's allotted now for that to get reworked and for C++23 now, that some thought will be given into what's the intersection between concepts, between pattern matching, and between contracts. Those things are all very closely related, right? If I have a contract that says that this function can't accept 0 as the argument, that's very close to pattern matching, where I could say, this function can't accept 0, but there's another function which can. And so instead of just asserting on violation of a precondition, you would roll over to find to find the other function for pattern matching. And even the terminology that, say, Bertrand Meyer used and that we've kind of settled out on using on concepts as far as stating requires for a concept versus requires for a precondition is very similar. And so I would like to see the ideas of pattern matching, concepts, and contracts kind of pull together into one coherent proposal. How do these things all fit together? They're all very related topics.
Right. Let's close with the last three questions. One is the most voted question so far in every C++ conferences, I think, with 11 votes, 11 upvotes, is by Victor. Let's close with a fashionable topic. Are you in favor of C++ breaking ABI? This is recorded, Sean. Think about it. This is recorded.
Yeah. So I think that first, C++ has never had a stable ABI. And that's been one of my pet peeves about C++ from the very beginning. I think C++ needs to get to the point where it can have a stable ABI, right? That can be through a fairly narrow interface. But if you look at the challenges faced right now, if you're building a piece of code like the product that I work on, Photoshop, I think last I looked, I'm probably getting these numbers way off, but it's something like 6 million lines of code for the core application, but it's got over 100 external components that get integrated into that, which are built, by a company now that's 20,000 people, by engineers spread out all over the world. And if you have to require, which is kind of the situation that we're in right now, that every one of those components is built with exactly the same set of dependencies, with exactly the same set of compilers, with exactly the same set of compiler settings, okay, in order to guarantee that you don't have ODR violations and that you don't have ABI breakage, that becomes a huge challenge, and that becomes something that prevents you from moving quickly and updating to the latest compiler, because you have to coordinate it across thousands of engineers and do it simultaneously. And if you look at the Photoshop code base right now, it's built out for Mac, for Windows, for WASM, for iOS, for Android, for Linux. You've got a very large set of tools, and just trying to keep the sources for everything and build that entire universe, and keep everything up to date and keep all the dependencies up to date, and being blocked because the third-party library that you have integrated, if you want to move to the latest version of the compiler, it shows 3 compilation errors with this library, and now you have to go fix them all and send a pull request when it would have ran with the old version of the compiler, is very problematic. So no, I'm not in favor of C++ just breaking ABI. I am in favor. There's a couple of proposals out there which I think are looking pretty good, for a path for C++ to have a stable ABI, and a way to guarantee that. Years ago, I worked with Apple, with Matt Oster, when Matt Oster was at Apple, to define what Apple would guarantee in their ABI, and it was a very minimal set. It basically just boiled down to a small handful of types, including exceptions. But if you look right now, right, the standard library on Macintosh is shipped as part of the OS, and so you are linked against that and constrained by what's in there as well, and constrained by the ABI that's imposed by that. So it's a it's a difficult challenge, and right now all the solutions that end up happening are hacks where we use symbol hiding largely with DLLs and violate ODR all over the place to make code that happens to work. And I want to get into a situation where we're not violating the ODR and we can write code that's compiled at different points in time that all plays together that works correctly.
Yeah. So last two questions. Next one is still by Victor. Is asking if so your take, does snake case for concepts create confusion with type traits?
I kind of wasn't a fan when I first saw it. It's kind of grown on me. I think it's a bike shed argument, right? I think the use of Pascal case in concepts was just largely a historic artifact that became convention, and I think being part of the language now, they probably should be snake case. Sometimes I get confused by it too, but I don't think it's any big deal.
Okay, last one, Sean. Then you are free. The last one is, will the same problem be in all algorithms making any comparisons, like set union, for example, and all the others?
Yeah, like I said, I haven't gone through to see how bad it is. I did a search to just say where is equality, where is CPP17 equality comparable actually used in the standard, and I couldn't find it used any place as a requirement within any of the algorithms. That is not true of like strict weak ordering, which is, wasn't removed because that's much more difficult to just pull out than a quality comparison. So I don't know quite how deep this runs, honestly. Like I said, I was looking at a particular problem and came across std-find and thought it was worth mentioning. I would like to see the standards committee take a more formal approach to how they're defining these things going forward. And the biggest breakage that I find, like even with std-find, with it not being written in terms of equality comparable now, is that as you're learning the code, you say, well, I've got this value that's equality comparable. Can I use it with find? And you have to go through the mental exercise to say, okay, well, find doesn't say it requires equality comparable, but it's a weaker set of requirements than equality comparable, and equality comparable will work with find. So it's that mental overhead where I think that the biggest part of the breakage is, right? One of the beautiful things about concepts was it gives you both sides of the puzzle pieces and tells you how they fit together.
Nice. So Sean, thanks. I think we are all set. I mean, it's almost time to. We are late just 4 minutes, so it's perfectly fine. I think you are. Thanks for staying with us tonight, Sean, because
yeah,
it's night over there. So thanks a lot. Many people on the chat are saying good night, Sean, and I'm wishing you good night. But anyway, you are more than welcome on the networking area. Even if when you wake up, if you want. So the networking area for us, they open all day long. So if you want to step into it just for a few minutes now and you want to get back afterwards, no worries.
Yeah,
and
I will jump into Remo here.
Nice.
My plan was to stay up as late as I can and participate in the conference. And so I will be around if anybody wants to chat.
Great. Thanks. Will be a C++ endurance for you.
There we go.
Just one information for the people attending, since most of them, many of them are asking. The way to reach all the links to YouTube in advance is going to this URL, as I said during the message. So online.italiancpp.org/direct if you want all the links to YouTube and also to Remo rooms if you have any issues. So that's it. Thanks a lot. Remember to give feedback. Thanks a lot, Sean, again, and let's meet at the networking. Now we have a break. See you at 10:45 for the 2 sessions in parallel, track A and track B. Thanks a lot, everyone. Thanks, Sean. Catch you around. Thanks.
Bye.
Bye.